the next task is, how do you evaluate whether an AI-ECG model is good or bad, and what are the frameworks that you need to use to read a paper so you can make up your own mind? So the reason we all need to know this is the number of AI papers that have been published have increased exponentially over the last 10 years. So I do feel that all clinicians need to have a framework of how to read these papers and make their own minds up, just as we've taught fellows and residents to read clinical trials and understand how to interpret clinical trials. We now need to have the skill set to understand how to read and interpret and critically appraise AI-ECG papers. So in the next 10 minutes, I'll hopefully give you a brief overview of how you can do that. I'm going to focus on a few things that I would tend to do when I read an AI-ECG paper. We need to understand what problem we're trying to address. We need to understand the quality of data used to train the model. You need to interpret the methods, interpret the results, and then you need to make your own mind up whether the conclusions match the results that have been presented. So like any paper that you read, if you read a clinical trial or an RCT, you need to first understand what is the problem that they're trying to solve and what is the impact of potentially solving the paper. And that should be quite well defined in any paper on AI-ECG. The more important bit is then to understand what has been used to train the model. And this you need to read the fine print, just as you do when you read a clinical paper and you try and dissect out the pros and cons in Journal Club. You now need to learn to do this for AI-ECG. So AI models are data thirsty. I showed you in the first slide, it learns patterns from the data you give it. So if you put in data that's rubbish, you're going to get rubbish out. So you need to firstly look at, when you read a paper, look at the methods and say, what have they put into this model? Where have they got the data? Is it good enough? Because if it's bad, then don't read anything else. Don't read the results. It's not worth reading. So a few things that you need to look at when you look at the data is how big are the data? So sample size, relevance, accuracy, bias, consistency, and balance. I'll come into each of these in turn. So I'm going to use one of our papers as an example of how to read an AI-ECG paper, which was published just a few months ago. So the first thing you want to look when you read an AI-ECG paper to work out whether it's any good is you want to work out how much data has gone into training the model. Now, of course, Manolis talked about foundation models that might need less data, but in general, you want to understand, is this a large data set that's gone to train the model, or is it a small data set? So if you read a paper and say, oh, we took 50 ECGs and we got this amazing model, you might think, oh, hang on, this probably is overstating what they've got here. So you want to understand how much data went into training the model. So in our example here, and you read the methods, we took 1.1 million ECGs, so a very large volume of ECGs. And with that kind of 7-figure sum, you might feel, okay, you have some confidence in what's going to come out the other end. Then you want to understand the relevance of the data. So are the data relevant? Here's where clinicians have unique insights. So if your task is to predict in-hospital mortality, but your ECGs come from general practice, that's not going to work. That's the wrong data set for the wrong task. So again, as clinicians, you can look into and say, well, what is the task and where have the data come from? Is there a match between the data source and the task you're trying to perform? Thirdly, how accurate are the data? We know that data that come from electronic health records are not perfect. How have they labeled the data? I said to you at the start, you have to label the circles and crosses. If you show a circle and you label it a cross, and you show it a cross and label it a circle, the model will get very, very confused. So how accurate is the labeling of the data that's gone into training the model? And did they use human interpretation to label the data? Did they use natural language processing? Did they use ICD codes? We know the limitations, all of these things. But again, understand where it's come from, how it's been labeled, and then you might decide whether or not the model is any good. So in this example of ours, our paper, we use ICD code. So we accept that the coding is not going to be 100% accurate. So there's going to be a limitation in the labeling of the data set that you give it to the model to train. Are the data representative of your population? Have the data come from the types of individuals that you will treat in your own practice? There are all these classic examples. Manolis alluded to that. There are all these amazing models that pick up malignant melanoma that work in fair-skinned individuals because all the training data come from fair-skinned individuals. The minute you apply it to someone of darker skin, the model fails. So similarly, are the data set relevant to you? So you're in the US, have the data set come from a rough relatively similar demographic that might be relevant to you, or has it come from, say, a Chinese population that's entirely maybe not so relevant to what you've got in your practice? How good are the data? Are they consistent? Are there any missing values? And are there any class imbalances? Do you have lots of one thing and not enough the other? So if you're predicting whether someone might have heart failure, but in your entire data set you have 2 out of a million who have heart failure, that's not going to work because it's not going to see enough heart failure ECGs to learn the signatures. Then you want to interpret what has been done. So we had a discussion a bit about whether it's supervised or unsupervised. Are you providing the labels, as we talk about, which is the vast majority of machine learning models, or is it unsupervised? So you don't tell it what the label is, you let it learn its own way of classifying patterns and breaking down the patterns. You want to look into how they've split the data to train. So when you have a lot of data, what you want to do is reserve some for training, some for validation where you test the model, and then you have this test set that you don't touch except for the very end where you test it once and you report your results. So you don't report any of these results because that's the training process where you try lots of different ways of doing the model. And then at the end, you test it one single time and you report that result. And that is really what they should report, not anything else. Ideally, they report an external test set. Have they taken a data set from another hospital to see whether it transfers well to another form of data set? In our example, we had a sort of split here that I will show you, but worth understanding how that was done. What AI approach was used? You need a bit of knowledge here. Did they use a convolutional neural network, which I mentioned and Manolis mentioned earlier? Had to use one of the other machine learning methods? Again, a bit more fine print stuff here. And I went over this. I won't to go into too much detail on that. Then you want to evaluate the results. How good is the model? So most papers will evaluate the results using one of these numbers. So if you're trying to predict a number, so a regression metric, so predict someone's height or predict someone's weight, you're trying to predict a number, not a category. They tend to present results in terms of error. So the bigger the error, the worse the model. So the mean absolute error, mean square error, different types of presenting the error, but you can understand how far off it gets when it's trying to predict someone's height. Or if it's trying to make a classification, so are you male or female? Are you high or low risk? That you can use true and false positives, precision recall, things that Manolis showed. So there are all these things where you measure the true, false positives, true negative, false negative, positive, negative predictive value, things that we're used to seeing in clinical medicine. So those are also similarly used in machine learning papers. We sometimes use a C statistic, that's a discriminatory variable. How good is it to discriminate a high versus a low risk individual? That you can do it from an ECG. I won't go into overfitting. And then finally, you want to understand whether it was tested externally. More and more journals will now not publish papers if you haven't tested outside of your setting, because as Manu said, you can end up training a model that recognizes features just unique to your own hospital, that does not generalize to any other situation. So it may work very well in Chicago, but once you take it elsewhere, it doesn't work. So people want to see whether not only has it been tested, but has it been tested elsewhere in a data set from another place, ideally another country, ideally multiple other places. And in our example, we actually trained a model of using Boston data, tested in 3 Brazilian data sets and 1 UK data set to make sure that it is generalizable, and you want to have confidence by seeing robust external validation. Then we talked a bit about explainability. You want to see, are the results explainable? It is something here that as a clinician, we can relate to in terms of the outputs of the model. Do we trust it? There's this excellent editorial a couple of years ago that says AI-ECG is a bit like magic and we have to trust the magic of the AI. But actually, as Manolis said, sometimes it's not so magical, it's doing crazy things. In this example of training a model to predict a wolf from a husky, what it's looking at is not the wolf or the husky, but the background. So if it sees snow, then it will say it's wolf. If it doesn't see a snow, it will say it's a husky. So you need to understand what the model is doing and have some confidence in its predictions. And we do things that I'll explain in another session about how you can break down ECG into different morphologies to work out what it's looking at. And then finally, like any other paper, once you've read all that, you want to understand whether this model is generalizable. Is it useful to your setting? Does it fit into your patient pathway? Is it a primary care or secondary care ECG model? Does it integrate into electronic health records? Can it work on consumer tech? So That's really an overview of how I would critically evaluate an AI-ECG model. And I think we all have our frameworks. This, I think, is quite a useful one to sort of think through the steps when you come faced with a new model and you want to understand whether or not it's worth your time. Thank you.